You knew that I was on the chat at 3. I was happy to see you there too. Whoa! Wait, who is this guy?
Thomas, would you
He's always been there. What do you mean?
Well, no, I've been there.
It's just been there.
I think we should. We
just don't look at it because, you know, we're looking ahead because we're studious. He's always been there.
Evan, what is that disgusting hydra you have?
No. Don't you worry. Don't you worry. It's not there anymore.
Please don't tell me that you're not.
I'm gonna do some course shopping. I'm gonna drop some of them. It's only at a very healthy 90 units right now, so I can drop down some of that.
You're like Jing, bro.
And I think what I've discovered
It takes 84
won't make
units
so
just to
life
drop
for the
them.
person that involves, but I'm going to do it anyway because I'm not that embarrassing parent. 1, 2, 3. Happy birthday to you. Happy birthday right to you. Happy birthday, dear Sadie. Happy birthday to you. Yeah. 11 days late. We're going to sing it 10 more times to make up for it. Anyone whose birthday was more recent?
I've been over this class.
Oh. Then I think it's you.
Alvin.
Yeah.
Alvin?
Last year, Alvin was trying to make for Edgerton when he was a student a voice-activated Pokemon. And it would have like a flamethrower. He always did flame. The whole thing was that when you would say his name, it would shoot fire. So he had it with voice recognition all set. Oh, you were there for that? Yeah.
Well,
Oh my.
You were there for right?
I was.
Yeah. Yeah. So they were trying to get him to recognize his name. And at one point, right before his name was said, I said, "Who's your daddy?" And when he said Alvin, it finally sparked. That's the whole thing.
Christian, you have bad news. I don't have my Apple.
You have your Apple Pencil? You keep leaving an Apple Pencil here.
I did not leave it here. I just had it 2 minutes ago. Oh,
Should it be safe? That's not
Me with
I'll be back.
the Apple Pencil shaped lodged in my mouth.
Alright guys, it's been a crazy week. I went to bed at 3. What time do you guys go to bed? I'm not competing, I just want to know. 11, 2.
Some of them went to bed at
3?
3.
Okay, so we were up, yeah. You 3? I texted the TA group chat at 3 in the morning. Carlos was awake. We're going to chill. It's going to be okay. We're going to do a little quick review of U-Substitution. Oh no, but who will pass the whiteboards? Just the samples can be handled both.
Right.
If not, get Mr. Summers, everyone whose last name is a plural noun should get to pass something. Yes, U-Substitution. When I don't sleep, I'm equivalently intoxicated, so watch out. It's going to be a fun class. This is with Chuck.
Whoa, you guys, no. No way you're replacing me.
Yeah, you're too long.
Christian, that's actually replacing me.
I know, I was very, very conflicted about it too. But
Oh, Christian, you're so sorry, but we have to let you off.
I really appreciate it. Merry Christmas. Like it's still in the dark. Okay. I have 27. I've been 5 in my bed. I have a problem. Okay. Hi. Hi, good morning. Okay, we're going to return to single variable calculus in a moment. But just remind me what was scarring your brain last week about multivariable and UV transformation. So if we want to go from X. I'm a dog now. If we want to go from to DUDV. These remind me of the appropriate conversion factors that we use.
Jacobian.
The Jacobian. Which Jacobian and where, Noah?
The Jacobian of UV to XY on that side. Oh, yeah.
Okay, and we put a determinant in that. Oh, it's wonderful. We're all getting sick too. In fact, we put a determinant, and I think I wasn't keen on this one. It's determinant's absolute value. This really should be this. But key thing here is we usually don't solve our change of variables this way. What do we do instead? We move it to the other side. So it really looks like dx dy is equal to 1 over absolute value of Jacobian determinant du dv. And during office hours, write down, or was it during the party? I don't remember, Leanne.
No, it was better.
Oh, right after class, oh, you was that. These are fun. These are the crazy Earth function things, right?
Oh,
No. I'm going to take the bait some other way.
It's polar.
Oh, you want me to go polar?
Oh, you should do it because some of us had trouble with polar.
I had trouble.
Yeah,
We all had trouble with polar. I'm not gonna
Really?
lie. Who is Idris?
This is a 2?
Negative x squared.
You do the negative x squared?
Oh.
Oh, that's
Some of
the
us
one
had
where you
trouble.
make it polar by doing. I barely remember it.
Yeah, we all want to remember too.
All right, hang tight. I almost want to take the bait, but I'm afraid. I don't usually run into that. It's like a Pokemon when you run into a challenger
Just
approaches,
sections
right? Like, okay, hang tight. You stay right there. I got my eyes on you. Okay. Eyes, but it's not going to be really complex. Eyes. Okay. Now, in single variable n, right? What did you do? You said that u was some function of x. And then what did we do from there? So we had our integral that was in terms of dx. And what did, well actually, what did we do? We took,
We had an integral of f of x dx, and then we made x a form of u.
yes, so we did du by dx is u prime of x, right? So then we said du equals u prime dx. We were trying to go from an integral that was in terms of dx to an integral in terms of du. Now we know du is u prime dx. Yes. So I'm going to write this down in a better way. U prime dx was du, but we like solving our integrals in terms of du. So what did we do? We moved this thing to the other side. And we got dx is 1 over u prime du. This is the single variable calc version of it, which is what you did in U-Substitution. I didn't take single variable calc last year, so maybe it's not so fresh in my brain, but you guys remember this?
Yeah.
Okay, cool. Remember this? Maybe. Okay. We're brought together by what we experienced together. We experienced that together. Okay. Questions? I would like to do a problem. I know. I would like to do a problem with UV substitution. And it is the following. It's a good practice. So if we have the region bounded by xy equals 2, xy equals 6, xy cubed equals 3, xy cubed equals 6. This is a warm-up, yeah. Doesn't Chem Ali always leave a problem on the board for you when you get into class? This is like that. It'll help us wake up again. Okay. Let's draw the region in xy space, and then do that sweet conversion to our happy place. What do we have? What does xy equals 2 look like? Yeah.
Y over 2x and y over 6x, so it's like a gas, what's it called?
Yeah, like y equals 2 over x, y equals 6. One of these.
An asymptotic graph.
Asymptotic, I like that. Okay. And then the other one?
Y is equal to the square root. Everyone's so creative with their ideas.
I know. Something like that. Cool. This is xy equals 4. Wait a second. I meant for this to be a 4. Okay, so this one over here is xy equals 2. This one over here is xy equals 4. This one over here is xy cubed equals 3. This one over here is xy cubed is equal to 6. Your skills at drawing it may vary, and that's okay, because we're not going to spend a whole lot of time in this coordinate system anyway. What do we want to do?
Switch it up.
Switch it up. Let's go to a happy place. In our happy place, u is what and v is what? Choose accordingly.
Let's make your one equation and
Yeah, this one was very much glaring at us. So what does this look like in pretty UV space? What was that?
yeah.
You're all saying it, but
Rectangle.
rectangle, yes, I know you're all saying it. Okay, so U goes from 2 to 4. V goes from 3 to 6. Something like that. I think technically this side should be taller. But that's all right. We know we got a rectangle, it's our twiddle. And rather than solve this out, let's just figure out the one piece that we would need in order to solve this out. What's that? The bounds, okay, so the, I didn't even say, let's find the area. So the area is equal to the double integral over the region R dy dx, or dx dy, but we agree that we don't like this, yes? So we go uv, and the price we pay for going uv is going to be, what do we need to do? What's the
scaling factor.
the scaling factor, so let's find the scaling factor. So our Jacobian going from uv to xy, otherwise known as duv by dxy. Okay, what are our partial derivatives? du by dx is?
Y.
Du by dy is x. dv by dx. Oh, even if you didn't know it. No, my mistake. I'm thinking about the Hessian. What am I saying? This isn't symmetric. Carry on. What is it? dv by dx is?
Y cubed.
Y cubed. And dv by dy is 3xy squared. Take the derivatives at 10 in the morning. Cool. All right. So we got that. What else do we need to find? A determinant. Yeah. And our determinant is equal to 3xy cubed minus xy cubed, also known as 2xy cubed. Going places. What's missing? And what are we going to do next? Oh yeah, that's 2v. Oh, 2v or not 2v. Now, we're going places because we have our Jacobian in terms of u and v. We have our determinants. We're in very good shape. We're in our first quadrant. Last thing is to set up the integral. Area is double integral. What goes in front of our du dv, did we say? Is it the determinant or is it? Ah, yes, it's 1 over. We're going to the other side. 1 over j uv xy over the region r twiddle. R twiddle is very pretty. R twiddle is very British. I'm going to the UK in 2 weeks, and I am going to find everybody very fancy. Arania, see, maybe I should go to a Spanish-speaking country and say, oh, hey, Spain won. They pronounce their S's and their Z's and their everything. Okay. All right, so we have 1 over 2v du dv. Bounds on u are
0, whoa, 2 to 4.
2 to 4. Yeah, nice catch.
3 to 6.
3 to 6. Okay, cool. It'd be funny if you had like a sports commentator like for the football matches, but like during class. Oh, he's putting the Jacobian in. Ooh.
Well, you know, is this like there anything that we can say? But because
Uh-huh.
du is independent of dv, can we
Yeah.
just separate and multiply?
You can separate and multiply if you feel comfortable with that, yeah. Your inner integral is just going to be what? 4 minus 2.
2.
So you guys got some practice in this. I'll show the boring way, and then if you want to be cool, yes, split them up, because the inner integral has got nothing to do with you. The letter U, not Y-O-U. No, why?
Well, no, it doesn't.
You're no stranger to the letter U being used in clever ways, because I didn't know your name was pronounced as Noah. That's pretty cool. All
I
right.
think I was pronounced as no.
Wait, Noah.
That's okay.
You guys do it, tell me that. All right, 1 over 2v du. So as far as u is concerned, this v is a constant, right? It's just a thing. So this really just becomes 1 over 2v integral du, which is just 1 over 2v 4 minus 2. That's a 2. That's 1 over v. And we can keep going. We might as well finish this at this point. outer is integral from 3 to 6 of inner dv, which is integral from 3 to 6 of 1 over v. Ooh, 1 over v. This is fun. What do we get when we integrate 1 over? Natural log. All right, so we're going to get natural log of 6 minus natural log of 3. And remember the cool logarithmic properties from pre-calc?
Divide.
Oh my god, yeah, it's natural log of 6 over 3, which is natural log of 2, which is e, which is 2.7 something, so the what gives you 2. That's pretty cool. Okay, so that's a little, I keep thinking there's someone in the back of the room, it's that for sake of thing. Remind me to tell you a story. Hi Vaughn, quick before I tell the story.
Oh yeah,
Say
2v in the Jacobian simplification. Can we always get like a value that can be like replaced with one of our existing like definitions?
By virtue of lecture theory, we will give it to you so that it's easily replaced. Yeah, it would be pretty tragic if it wasn't.
Do you have an exam where you don't have that, or you kind enough not to?
No, it's not that I'm kind enough. It's like you don't have computers on you, so yeah.
Oh.
This is gonna be. No, I'm all in all, how was the piece set, by the way? Yeah.
We spent 3 hours looking for some random ancient proof that was in the first piece set as he decided to.
Noah.
Which one?
ChatGPT.
ChatGPT.
No.
It took 10 minutes.
Gaussian short, yeah, no, so
3 hours.
I should have,
ChatGPT did it.
I should have given you that
That's not a.
in the problem of the hint.
I want Gaussian short.
Now I know, okay,
I
it's my first time doing it, you gave me a hint sometimes, I apologize.
You guys
We'll go easy on the brain. But no, like in general, piece set 4 is posted and it's much less rough. Why? Because I wrote it at 1 in the morning.
I did.
So I only had so much energy.
You saw that I proved it.
Okay.
I don't know, we weren't getting anywhere.
All right, any other tomatoes you want to throw at me for piece set? I you don't look very happy with it. We should put googly eyes in my house. She's got the googly eyes.
It's our problem. All for the property.
Okay, we ready? All right, this is UV. Now I need to bring us toward a new topic, unless there are any other things we want to talk about.
The Gaussian.
The Gaussian.
What is it Gaussian again?
Gaussian's fun. I actually prefer them in 2D. I wanted a 2D one.
You have to do it.
Oh, that's right. That's what you turn into 2D. Yeah.
What is it Gaussian?
It's nerd sniping. They call it nerd sniping. When you're trying to nerd snipe.
Are you going flux now?
No, you don't want to go flux. What flux is going on over here?
What are we doing for that?
What's the erase?
We had learned that. I was like,
Nope. We did not.
It's like there's a slope field. Yeah. There's also things such as a vector.
So we're going to. We've got 5 more lectures, and I want the last 2 to be applications and like high-level stuff that I will still ask you about on the final, but not in detail. In order to do that, we've got some ground to cover. But I want to get us through triple integration. It's not so scary. It'll be okay. There's something called convolution, which is also not as scary as it sounds. Convolution, like they might as well call triple integration headache or something. I'm going to try to not make it headache, even though I'm on date row right now. So, what are we going to do? We are going to remember, as always, just like the 10-year-old in your brains who is judging you for your life choices right now, we're going to remember where we came from. In high school, we had, remember this? Y equals fb of x, y equals sa of x. I'm using MIT this class notation on here, but you remember the idea? You remember? And so we're going here from C to D. We have this region here, and the key thing was that in high school, you said that the area is the integral over one variable, single variable integration. Oh, very cute. fb of x minus fa of x dx. And then you came to MIT. And then what? And then you were told, hey, let's do this as a double integral. Because we can. And that became the integral from C to D of this stuff, but this stuff we learned that we're going to write it as itself as an integral from fa of x to fb of x, this thing, dx. Okay. We're now going to formalize what each of these integrals represents. And to do that, we're going to go a little bit more abstract. Okay. I'm going to put my little prize over here and hide it for now. Okay. What we're going to do is we're going to look at this as the following. Notice I'm drawing extra slow because I haven't had all my coffee yet. And I think metaphorically, none of us have had our coffee yet. Okay. We are integrating to find the area of a region R rather than call this the x-axis, I'm going to call it L.
Who's that?
Who is L? What does L stand for? Length, I guess. It's length. Usually this just means x. But what I'm really driving at is that this over here, this I'm going to call B. This is the shadow in x. So we're trying to integrate over this region, R. And we are going to integrate over the shadow. The shadow of this region is length. Right? In 2D, the shadow of 2 dimensions is 1 dimension, is a length. Bear with me for 1 second. Area is integral over the shadow. Quotations. F of x, f of x, dy, dl. So this is the integral over the shadow of our region of length. Of height, sorry, of height. Right? We're integrating the height over the shadow. This really wouldn't be helpful if we weren't about to bring it up to 2 dimensions, to 3 dimensions rather. So we have derived double integration in terms of this notion of a shadow. The shadow of a 2D region is a 1D line. And those are our outer bounds of integration. Okay, questions? I want to make sure we're on board with this. I want to check if we're on board with this before we add a dimension. This doesn't have to make sense. I haven't had my coffee, guys. What did Buzz Lightyear say? Flying is falling with style. This is where you show me how lost we all are. Hi.
Can you put B shadow there, just have the inner bound is the leftmost point, and then...
Yes. Yes, so from here to here, right. That here, that's our shadow. In fact, historically, I've made the shadow blue, but I think I'll formalize that more when we get to it. Sure. Okay, yeah, that's B, our shadow. Okay. Yeah, more questions here. What does this become when we do double integration as we've seen it? What is the shadow of an XY region?
Usually it's just bounds.
Yeah, this is just bounds in X.
And this gives us an area because it's 1 dy dl. Right?
Yes.
Okay.
And L is usually X, yeah. Just like the dimensions, the axis of the shadow. Bless you.
I'm not a lecture here, but if a double integral of 1 dy dx gives us an area, but the triple integral of 1 dy dx.
this a volume?
It would, the shadow, now this is excellent, this is exactly where we're going with this. Now we're gonna progress into 3D. Shadows of 2D regions are 1D. Shadows of 2D regions are 1D. Shadows of 3D regions are 2D. So, everybody get this down? No complaints if I erase now? Okay. We continue the progression. We plot 3 axes, we've grown up. Let's see if we can pull this off. I need some yellow. I need some green. And we have in 3 space our beautiful Aladdin carpet. This is FB of XY. And we have our other slightly more plain looking rug FA of XY. And we have some little slice of this region here. This is going to be our region. This is a volume. Volume D. And if we were only in a world of double integration, meaning last week, in my notes that I teach during the semester, I have like October versus November, and this is literally Monday versus last Friday. Welcome to Interface. So in last week mode, you would say that this volume is the double integral of FB of xy minus fa of xy dA. And what would your region of integration be?
Whatever we saw in the XY plane?
Whatever you saw in the xy plane. That is beautiful. Yeah, it would be this. This thing over here, that would be R, right? So you're integrating this from here to here, so R. And this actually brings us to a very, very, very nice realization, which the last part of the last p-set problem began to bring us to it. I think I'm not going to have that one very soon, because I just end up doing it in class. If we follow the progression of things, as we went from from single integral to double integral. If we go from double integral now to triple integral, knowing what we know about shadows, what do you think this enlightened approach to this volume looks like? We always have our outer balance in terms of the shadow. So we know that we're going to have double integral now, where R is the shadow. Yeah, maybe that should be blue. Okay. Of our inner variable, dz, where z goes from fa we integrate that over here. Okay. All of this to say, we pick an inner variable of integration. In this case, it's going to be z. And we take the integral over the shadow of that integral. So the shadow of the 2D region is here. It's our xy situation. Okay. Questions? That did not have to make sense. I have to tell you, I have a really big headache this morning, and I'm just realizing right here, standing up right now.
Number 7, we kind of gave us the R, but how do we actually see the R?
That is an excellent question. It is, for whatever reason that you're doing, it is the projection, the shadow, I don't want to use projection that you fit, of that region on the xy plane. But more generally, it is the shadow of the region onto the plane formed by the outer two variables of integration. Usually, we're going to do dz, dx dy, or dy dx. So that shadow is in the xy plane, so not always the case, yeah? V is volume.
Volume is what?
Of this region.
That region is like.
Oh, D, yeah, like the 3D space.
How do we define this contour?
How do we define the contour? We mean, in a specific problem, we would give bounds. Like between this surface and this surface and this plane and this plane. We would give you specific constraints. This is like a more general way, but yeah. Questions are
How would you do planes, like if you have a square that we divide every plane, so like let's say,
I'm going to give you one. We're going to do a tetrahedron volume. I think that'll help.
A tetrahedron.
Yeah.
Why don't you do triple integral versus double integral?
Oh, only for the sake of
Lecture theory.
yeah, lecture theory. But that's a really cool point. Another way to write this would be the triple integral over the region D, right? That thing of dv.
Wait, so if we put a volume, if we put another function inside of that,
Uh-huh.
is that hypervolume?
It depends on what you want to put inside of it. What are some applications of triple integrals, you think, where the integrand isn't just one? What do you think?
Density.
Well, then you can use density to find
Volume. Oh,
mass. Yeah, we got the volume. Yeah, sorry, all good, all good. Okay, so on and so forth. And actually, to your point, Sadie, this that we did over here, this can be written as just a double integral as you know it over the region R, which is this, dA. Hi.
If the volume doesn't come to the xy plane,
Uh-huh.
how do you find the shadow of the greatest, like, cross-section?
Yes. So we're gonna do an example of that. But you do find the shadow of it is that cross section of the xy plane.
So it doesn't have to be the bottom one. It can also be the top one if it's bigger.
Well, that depends. That's a really good question. I made FA flat, so that's leading us into some trouble. Give me a sec, because I think the tetrahedron problem will get us there. Vaughn, you got a question?
Yeah, like, what is the, I guess, significant difference between like doing the double integration version or the triple integration version?
Do you mean the
Like the application.
this versus this, or just doing this?
The top versus bottom.
The only time that this really becomes a situation where we want to do this more, other than saying it's for practice, is if we want to integrate something that isn't just volume. Like if you wanted to find mass or average value, your integrand starts to get very involved. In which case you're going to want to do the integration over the three variables. All right. Same thing with double integration. At a certain point you're like, well, I guess it really should be a double integral. Okay, more questions. All right. So you have another question? I thought you had. Okay, so this is good stuff. Let's actually get our hands dirty and try something with this. The only other thing I will say before that, I have a weird backroom situation going on here. Lecture 11, front page, and then I get to my next page. Lecture 11, front page. Deja vu. Okay, that's funny. Okay, so what are we going to do? Triple integration is scary. It looks scary, but it ends up not being as scary because it's just a double integral inside of it's an integral inside of a double integral. Let's work this out. Let's do the tetrahedron. So the question is as follows. So find the volume of the tetrahedron bounded by the plane x plus y plus z equals 1 in the first octave. Using triple integration. This is a problem that will allow us to see shadows, bounds, all of the above. We're going to walk through it step by step because this is the procedure that will get you through all triple integration problems in Cartesian layer. Okay, so first step, so important that we call it step 0. Draw it. Okay. But even before we draw it, let's think about it. What is this? What do you see? Describe what you see. Like those weird psychological ink blot tests, slightly less vague.
I see a graph.
Ooh, it's coming to him. What does it smell like?
An apple. I can feel the apple. It's telling me that we gotta draw the graph or something.
Okay, so I'm gonna draw some axes while you figure out that apple.
And that maybe we could use values like x equals 0, y equals 0, x equals 0.
Oh, that's really clever. All right, give me the axis intercepts.
Oh, I have to?
Well, I'm speaking to the general air, the spirit in the room.
0, 0, 1. 0, 1, 0.
Wow, Mickey Mouse!
1, 0,
I
0.
knew you'd come through, Mickey Mouse. I was thinking about you all weekend. All right. Yeah. Okay. I see a piece of paper slicing my axes over PVC pipes.
I have future vision. I can see the triple, you writing a triple integral next and asking us what to do after that.
Well, you're a clairvoyant because I haven't even figured out the planes that bound this thing. I have a plane, but what other planes bind this? Keep us bound. Box us in. What's the word?
Box.
Patty Christie. What do we have? We have that slanted little thingy thing. And what else?
X equals 0.
X equals 0, y equals 0. Yes, I'm not even trying. I shouldn't try to do anything. Yes, we have the XZ plane, the YZ plane, and the XY plane. Right? Think of a shape. Think of a tetrahedron. Think of like a little pyramid sort of thing. You got a plane here, a plane here, a plane here. Isn't that the shape at the front of the chemistry textbook? Who opens the chemistry textbook? Yes, it's very pretty, the tetrahedron. I don't know about the chemistry textbook. Okay. So that's our shape. Okay. Does anyone not see it? Because I understand that it's tricky to visualize when I'm putting this on two-dimensional paper. But okay. All right. Now, sorry, no, I interrupted your vision.
I know.
Step 1. What is our height? What variable do we want to use for our height? I like the idea of z2. Okay. Height is equal to z, which is what? If we're entering our region, what is the lower bound on z? 0. And where are we exiting this region? On this plane, right? Which is what? 1 minus x minus y. Now that we have defined our height, the next step is to define our shadow in the plane of the remaining variables. If our height is z, that means that our shadow, which I keep saying ought to be blue and then they'll do it, our shadow should be what? Should be xy, in the xy plane. Okay, so now what we're going to do, hang tight. xy. Let's set up, tell you what, before we do the shadow, let's just set up our inner integral and then we'll spend time with the shadow. Okay, so our inner integral is an integral over which variable did we say? dz. Do we have an integrand other than 1? No, because it's volume. And what are the bounds? 0 to 1 minus x minus y. Now we need to do our outer stuff, which is in terms of the shadow. So let's dedicate some time to the shadow. Okay. So that brings us to step 2. Set up outer integrals in terms of shadow. Okay. Shadow is xy. The xy plane, and we are going to draw the shadow. Okay. What does the shadow of this region look like in the xy plane? It's a triangle. Give me some vertices. Yep. Okay, so here is our shadow. Our region R is our shadow. Okay. 0, 1. 1, 0. We might as well quantify some stuff. This line is y equals 0. This line is x equals 0. What about this line? Yep, y equals negative x plus 1. Does everyone see how we got negative x plus 1? Right? Negative slope. Y-intercept is 1. We're in good shape. Okay. Now remember, and that's the magic of why triple integration isn't some crazy newfangled thing, is once we have our inner integral, we end up just doing double integration, which at this point is a little cozier, because we like 2 dimensions. It's a little more manageable. So we're going to say that our outer and middle integrals it's the double integral over that shadow R of our inner integral dA. We're going to put our dA in there. And we can actually work this out. We know what these bounds are. So what does dA become? How do you want to integrate over this? Pick an order. dy dx? Okay, I like that. Wait, what now?
I always said it's d. You just like.
Oh, I have to say dy, like the end of your limit.
I actually want to say dx, dy.
You want to say dx, dy? Okay.
No.
Ooh, popular uprising. Okay. dy dx. So what is our lower bound on y? 0. And our upper bound comes down here. Okay, and our bounds over x now? 0 to 1, right? We've taken care of the dependency between them. And all of a sudden, we've broken up this complicated looking thing into simple pieces because we've written out a double integral that we know, and we've written out a single integral that we know, which means this whole thing becomes a ring. Most of you don't have ringtones. That used to be a thing in the aughts when people would, here in the aughts, everyone's ringtones is loud, but everyone just has stuff on vibrate and that.
No, we don't respond to it.
Ah, okay.
Is that you?
Oh, Scott. Oh, you should have picked up. Oh, I gotta tell you stories. I used to call them back with Python code about 100 times a minute. And, oh, it's a story. Okay, so. Yes, I was heavily inspired by that. I also used to respond to the Nigerian Prince emails. Oh, we gotta talk more. All right, guys. So what is this integral as a whole? So what does it look like now that we've expanded it out? Integral
of dz,
dz,
dy, dx,
yes, okay.
from 0 to
Uh-huh.
1 minus x minus y.
Uh-huh.
And there's something I'm going to together. So then from 0 to negative x plus 1, from 0 to 1.
Amen.
That makes
Okay. Beautiful. And what was this dy dx, remember?
dA.
dA, yeah, that was our 2D situation. Okay. Here, more than ever, it is important to keep track of the inner, middle, and outer integrals, else you will lose yourself in variables. So I'm very, very picky about this when I work with math. The next step is simply solve. So we're going to say, first we're going to do inner. Inner is integral from 0 to 1 minus x minus y dz, which is z from this to this, so it's 1 minus x minus y. Did I do that right? Yes, okay. Middle is integral from 0 to negative x plus 1 of 1 minus x minus y d. D what? dy. We do y, right? Yeah. I mean, all right, just making sure. We could have gone with no one wanted. Okay, so that's going to be what? That's going to be y minus xy minus 1/2 y squared. And here I'm even pickier. I write the bounds with the variable. Y is negative x plus 1, y is 0. Otherwise, I'm going to lose track of this. Everyone remember how to integrate with respect to y if there's an x? What do you treat the x as? A constant, just like when you were doing partial integration and derivatives. We're going the other way up now. Okay, cool. And so we plug this in, and ultimately we will get dot, 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 hey, that's not half bad. 1/2, 1 minus x squared. And lastly, we will do our outer integration from 0 to 1 of 1/2, 1 minus x squared dx. Hey, I think U-substitution is going to make an appearance. How do you guys used to solve this?
Let u equal 1 minus x.
So
Let
du
equal negative 1.
dx, yeah, negative 1 dx. And so, move it to the other side. Dx becomes negative du. You could do your whole algebra, and you end up with 1/6 is the outer integral. Are there any constants in front of this? Any other work we need to do? No, right? So that's our volume. 1/6. In fact, you can prove this, but the volume of a tetrahedron with side lengths A, B, and C, the x, y, and z intercepts A, B, and C, is ABC over 6. And you can prove that, but we won't. But that's a rundown of triple integration. Okay, questions? So what's the simplifying factor here? What do we do to boil a triple integral down into simple steps? You draw the 3D region, and then what do you pick? Pick a variable for height. In our case, we pick z. And then the rest of it is just a double integral over the shadow in the other two variables. Yes. Now, I picked z as my inner variable, but that's not the only way I could have done it. Give me another example. Could have done y. So let's say that our inner integration was over y. Then what is our shadow in? The xz plane. And if we draw the xz shadow, we get a line there and do the same exact thing. And what should we have gotten as our answer if we did it that way too? 1/6, same idea, right? It should be agnostic. Hi. Excellent question. Excellent question. Give me a second.
If it's on the xy plane, you set the variable that is your height equal to 0, and you look at it on the other two variables, right?
Yes.
So in this case, we set z equal to 0, and then we looked at the xy plane. Oh, that's true. If it wasn't.
So, for example, in the piece that we had a question, the paraboloid 4 minus x squared minus y squared, right? And we wanted to find the volume there. Say it. The largest part is also. Oh, I see what you mean. I see what you mean. For that we would take an xy plane slice, right, at
That highest.
that height. Oh, because we would tell you the bounds. We would tell you, like the paraboloid starting at z equals 1 to like the top.
If you graph it, you see it? Is the idea? Is it if you graph it, you see it?
Yeah, let's, and why don't we do that? Let's just grab some stuff.
Let's do paraboloid.
Let's do a paraboloid, I agree. Okay.
Would we ever get a problem where the stop of the paraboloid is not a flat plane and it's instead like a symmetric plane?
Oh!
Yeah, I mean, I don't see why we couldn't ask you to find the.
Because that's not how you wouldn't do that test because
Yeah,
you're so
you
high.
would do that to a plane.
How can I say no to those smiles? Okay. That'd be a great piece of. I'm running out of piece sets.
Why did you do that? You're right. First you're gonna scam like
Yeah,
you
you're right.
Then you ruined our
This piece set is the last one. Oh no, yeah, don't sound too sad. Wait, guys, I have a pop culture question for you. What does surreal means? Are you familiar with surreal memes? Like the absurdist ones, the very absurd ones with the. Yeah, I got into that. I feel like it was brain rot, but it was wholesome because it was still human made.
Homeless ticket? I mean, homeless pizza?
No, the I'll have to find some.
Are you talking about AI?
No, pre-AI.
Oh, okay.
Here, surreal memes. Oh, I think finally. I'm talking about these very strange ones.
Oh, yeah.
Yes.
Yes, they're absurd. I don't know what to do with them.
Look at these, do not water your fingers.
Those were different.
They don't make any sense. Can any, this is something. You may consume 3 beans, but no more. They will know if you consume more. This was the thing. I remember in the early 2020s, I was on Reddit during COVID, and these showed up all over the place. I spent too much time. But this was brain rot when we still make it. Now we can just make
What is this? Dude, this has nothing to do with what?
It's not true choice. People, the cheese stick have to turn.
You know what?
Okay, I have calculus.
I need to listen and learn.
Here's a paraboloid. So let's pick some regions. Z is 4 minus x squared minus y squared.
Wait, no, we want the other way. We want to go upwards.
You want to go
For
upwards?
Lily's example.
Fine. Yeah, I agree.
So x squared plus y squared equals z, but then up to 4.
Yeah, okay, so let's do this. This, and then up to the plane z is equal to 4. Okay. And we were asking you to find the volume of the region bounded by these two surfaces. So it's 3D, yeah? We're the inside, we're in between them. Okay. So what do you want your inner variable of integration to be? Height, right? So z. Okay, what are the bounds on z? Z enters at?
0.
It enters at x squared plus y squared, and then exits at 4. Do you all see why that is? Yeah? Okay. Now, what is our shadow? I'm really glad you asked this, Lily, actually, because I think I exposed some oversimplifications in what I was saying. What do you think our shadow is going to be?
There's no plane. That's on the plane.
It's a circle.
It's the circle. What is the circle? X squared plus y squared equals 4. Right. It is the xy plane of the intersection of the two curves, the two surfaces. So what is the intersection of this plane and this paraboloid? It's the circle, right? So take that circle, imagine it here on the xy plane, right? And over that whole region, you are integrating that volume inside.
And so if we have like a sphere, we're looking at the greatest xy contour.
Yeah, you're looking at the greatest xy contour. Does it make sense why? If we only looked at where x squared plus y squared intersected the xy plane, what would that be? 0, right? And that doesn't make any sense. But you know, from a visual standpoint, that you're adding up a bunch of little heights within that circle of intersection here. Okay. Cool. More questions? Ooh. Z is equal to 4x. Maybe plus 2. Something like this. Very good question. All right, everyone. What is the intersection of this paraboloid and this plane? Is it a circle or is it something a little wilder? And how could you check what it is?
By actually plotting it.
Yeah, you find the intersection of the two. What's the intersection of x squared plus y squared and x plus 2? It's a whole bunch of algebra, but if you look at the shape, what are you led to see? Is it a circle?
Technically,
It's an ellipse, right? It's an ellipse. So that ellipse becomes your shadow on the xy plane. Hi, Olivia. No, actually, if you shine a light from above,
Yeah, would you see something straight down?
would you? I don't think you would.
well, let's just graph it.
No, because look at the points, right? It's going to be wider on one of the axes than the other.
Wait, why don't we just graph and see?
Yeah. Okay. I mean, so what do you want to graph?
X plus 2 is equal to x squared plus y squared.
Okay.
Technically, that's the part we're saying.
Yes. So let's do that. X plus 2 is equal to x squared plus y squared. Ooh.
Oh!
Oh. Ooh.
NT was collapsed.
Hang tight. Yeah, no, I think I've made a mess. Hang tight.
No, but it's like an off-center circle.
Yeah, but it's
It is an off-center circle. Oh, so maybe these... Oh, wait.
And it
It is a circle. Yeah.
It's just an off-center.
Yes. It is. So on the plane itself, that slice is an ellipse. But on the plane where it intersects on x plus 2, it is an ellipse. You see that? Right. But on the shadow on the xy plane, what is it?
A off-center circle.
It's an off-center circle. So our shadow region is that off-center circle. Yes. And that gives you the xy relationship of where that intersection is. We could do this in class. Maybe that's... All right. Do you guys want? Why don't we work this one out during class time? Yeah, and then I'll delay doing polar stuff in 3D until Wednesday because we probably shouldn't introduce that right now anyway.
Okay, yeah.
Okay, let's do it. So, our question is the following.
What is the volume of this?
What's the volume between these two regions? Yeah, this is going to be good practice. So feel free to work it out on the whiteboards too. It's a good one to work on together. I'll do some stuff on the board to lead us, but also do some stuff on your end. We can figure it out. Okay, so we want to find the volume between z is x squared plus y squared and z is equal to, what did we say the slope was? X plus 2. Okay. Let's follow our steps. What's our first step? Draw. Which we've done. Cool. Okay. The next step.
Find our z.
Yeah. Well,
Or our height.
decide our height. We want it to be z. Okay. So inner variable is z. So what's our inner integral? Integral over dz. What are the bounds on z? We're entering the region at. Where are we at? If we're finding the volume in between these two, where do we start entering our volume? I want a convincing answer. Whether or not it's wrong is okay. Where are we entering on z? Where are we entering our region of this integration? At the paraboloid, right? We're entering at the paraboloid. So x squared plus y squared. And we're exiting at where? X plus 2 at that plane. Okay. Step 2, let's focus on our shadow. Our shadow is going to be the shadow of the intersection of those two surfaces on the xy plane. So what is the intersection of these two surfaces?
When they're equal to each other.
When they're equal to each other. So z is x squared plus y squared, which is the same thing as x plus 2. Okay. Let's keep going. Oh, this is going to be fun. So what are we going to do? Oh, more so we're trying to see what that shadow looks like on the xy plane so that we can define the bounds. And I don't know that I see it right now. I mean, we could, yeah, sure. So x squared plus y squared, or x squared minus x plus y squared plus 2 equals 0. There's a whole, or equals 2, equals 2. This isn't very pretty, but maybe this makes you want to go to some coordinate system. You go polar? Yeah, I hear the about Canada Seltzer. So r squared cosine squared of theta minus r cosine theta plus r squared sine squared of theta equals 2. What can we do over here? This becomes r squared minus r cosine theta is equal to 2, which means r, what do we have? R, oh, this is just annoying in any sense, but that's okay. R minus cosine theta is equal to 2. Oh, this is
Yeah, you can just complete the square.
oh my god, you guys love completing the square. Yeah, please get us out of this mess.
Oh, okay, okay.
Okay, you want to complete the square? What do we do?
It's 9/4 is equal to x minus 1 squared plus y squared. Or do you want the steps to get there?
No, I trust you. X minus 1
Half
squared plus y
Oh,
squared.
one half.
Where?
X
Here?
minus 1 half, yeah. Is equal to
Okay.
9/4.
Yes, completing the square is not the forte. But I'm very happy that you did this and you saved us from polar insanity. Because maybe we just keep this and we don't actually do the algebra at a certain point. Okay, so that's our shadow. And what is our shadow in English?
Our shadow is what we see on the xy plane, or our area.
Yeah, and it is a circle of radius.
9/4 at the point 1/2.
Wait, what's the radius of the circle? 3/2. Ooh, that's okay. It's a circle of radius 3/2 centered at
1/2 0.
Wouldn't it be plus 1/2? Because it's negative.
Wait. Because it's x squared minus x. So it has to be minus 1/2.
yeah. I'm betting it should be minus 1/2 because when we plot it, we also consider it to the right.
I see.
Yeah. So
Yeah.
x minus a half square plus.
Think about
Yes, we get along here in interface, don't we? Okay, very cool. Okay, cool. So our shadow is that circle. So what does that mean? That means that if we were to define our other outer integrals, they would be over the region R, again, of our inner situation, which was integral over z, x squared plus y squared, x plus 2. And what do we have over here? dA. And our dA is, again, that very special circle. Okay. And so if we wanted to, we could plug it in. We probably want to go polar or something. I don't know. This wasn't a lecture theory example with the numbers because the circle's not very pretty, but we would be able to solve it. But it gets the concept through, I hope. Please ask more questions. The more questions you ask, the more we slow down too. It's good stuff. What was that? Would I like to finish it? I would not like to finish it. Oh, yeah, absolutely. Well, yes, so plugging in the bounds, yeah, I don't see why not. I mean, so what would we do to find the bounds, even if we don't actually then do the integration? Well, you want to go polar, right? Or is this a painful polar situation? Say it. The radius is tangent of the origin, so it ends up, yeah.
Like, how would you, there was one problem
That was a convenient one where it was offset by the origin by the same amount as its radius, and those clean up really nicely.
But this would be.
This was not like that because we came up with it by hand. No, you wouldn't get this one on the exam. You get one where the R is very easy to write in terms of theta. Yeah. Yeah, we let this one be a conceptual one.
Is this our segue into stuff that would look good in polar?
Yes, it is.
Or do we have, oh, we only have 5 minutes.
We only have 5 minutes, so what do you guys want to do instead?
We should do the thing from the
Yeah,
beginning of
I mean,
class.
what's that?
The thing from the beginning of class.
Oh, no, did you erase it?
No, I didn't erase it.
And so, oh, yes, you did.
I didn't. Oh, I'm like a magician with the little extra little point.
Get to work.
Get to work, yeah. Okay. No, I'm gonna cheap out. Let's do it together.
Together?
This 37 point something or other doesn't help us too much anyway in terms of doing, so what is this?
The integral.
E to the negative x squared dx. You can do this one by turning it into a double integral.
Can we? From the little integral of that bounds to the 0 to that function? No.
What about the hyperspecific square?
Say again?
What about the hyperspecific constant?
We'll plug in
We'll
that.
throw in the hyperspecific constant at the end. Okay, so this is I prime or something. All right.
So we're going to go double?
This ends up being one that is nice to do double. But do people know why? I haven't done this one in a while, but it's fun.
Why is it better than double?
Because it exploits certain nice properties. Wow, I haven't done this one in a while. I don't remember exactly what the little magic trick is to get it to go.
Square root
Yeah?
You squared the term d1.
Say it.
You squared the term into d1.
You squared the term what?
You square I, square both sides. And then you can turn one.
Ah, okay. So we're going to say I prime squared is equal to? Oh,
Tommy,
this.
why do you know this?
That's not the solution. I'm not
Yeah, actually, he is the MIT.
Okay, so negative, you're saying this?
Yes.
And you want to call that y instead?
Yeah.
Okay,
Is such true?
okay. And then what? Ah!
Oh, and
Then
then you have to add them together. You can, when you multiply.
Yeah. And why can you do that? Why does that clean up that way?
When you multiply your two e's, you can add your hours, and then you can go polar.
Yes, and we agree that these integrals are independent of each other, right?
Yes.
Okay. So we're saying this is e to the negative x squared plus y squared
0 to infinity.
dy dx, negative infinity to infinity, negative infinity to infinity. All right.
Wait, then what does our power become? Oh, our radius is literally 0 to infinity, or 0 to 2 pi.
Well, yeah, exactly. I was going to say, what do you want that x squared to y squared plus y squared to be? What does this make you want to go? Polar. Which is actually really cool because it unlocks a magical relationship. If we go polar, what fundamental constant are we going to start to see? Pi. We're going to see pi, and we were an exponential land. And we know from all the Euler insanity that pi and exponential have got a lot in common. Oh, this was fun. This was really fun. Okay, so what do we have now?
There's the integral of e negative r squared,
Uh-huh.
the r d theta,
Okay.
from 0 to infinity.
R goes from 0 to infinity.
Oh, negative, yeah.
Yeah.
Well, yeah.
And theta goes from?
0 to pi.
Why'd you switch that?
No, because now it's r.
Because now we're not theta land. We're polar. Right, and so R is this?
And then 0 to 2 pi. We can just multiply that 2 pi out.
We can multiply the 2 pi out because this has got nothing to do with theta. And what else do we get? So we get
2
pi.
pi times the integral of e to the negative r squared r d theta.
Whoa.
Okay.
Yeah, I mean I did the d theta out there.
Is it time for limits?
It is time. Yeah, how do we solve? This looks like a
U-sub.
is this a U-sub?
Yeah.
Damn, it's a U-sub. All right, guys, lecture's over. Come stick around if you want. This is fun. Please bring markers and whiteboards and all that stuff.
Christian, keep going. Literally, R squared.
Why do I call this? Silly stuff.
Whoa!
I just the thing is you end up finding out the area on the developer.
I don't like how.
Oh wow, Leo! Wow. I'll be
Because that's how I learned it. No, you make sense. Yeah, you can make it.
I guess I was offered to do this problem very specific.
I know, like if you do work along this path, you think you're gonna this length, I get it.
It's a rectangle.
I get that. This makes sense. Now I'm stuck how I get the metrics. Because I have never seen it.
It's not your problem, no.
That is the question. And I'll figure it out.
I think I will say this is like
Oh, okay. For the first part, if I understand conceptually that it was done through the lines path, like I do have the interpreted dx, because that's the only direction I'm going in, and I just do the force.
Because
I know that conceptually. Can I just do that? Is the whole point to
you would read that
because if I already have
multiplying this integral by itself, right? But you don't have to call this any variable, you call it T2. So I can just call them two different variables.
I think the idea is
Because they don't have one regular, like the x's and the y.
No, James, don't leave.
Oh, I think
I'm
so
just not a better person.
and then you can
Text me all those options.
Oh, that for real? Oh, that's great.
And that's like that same principle is how you can create diversions.
I know that as far as the y is here, like x is a constant.
That's gonna be
Like
good.
this can also be.
I'm hoping we can talk about it, but there's just like the fundamental terms of integrals, it's all just like they all relate to this one idea of
They
like,
do, yeah, no.
you can integrate over a differential operator on a field in order
Because
to
this integral, do
equivocate
you
that
agree with me that
to
this is a number?
boundary condition of just
This result will be a number. So x is in that basic situation.
Is it okay
This could be a
if
y,
I
this
did
could be a u, this could be a w, this could
that
be a
r
porcupine.
is equal to
that. So
I
this
said
is the
dr
same thing.
equals ds.
This square has the same thing as this
I
times
think
itself.
that's pretty complicated.
But the second integral, I could write it in terms of any other variables. Because I'm going to get a number at the end of the day, right? So I chose the number y. It doesn't have to be y, it could be anything
Let's
else as
see.
well.
Y'all didn't get to a cylindrical and
I love symmetry, right?
Because I'm summing over all the y's anyway. So that variable never exists after the operation.
you know what?
I want to see
what I mean?
I want to see what it
Yeah.
is. And just,
Right, so I just chose.
No, he's not.
Listen, at the end of the day, if I have any variable squared plus any other variable squared, I can come up with a coordinate system in which the sum of the squares of those is the distance from the origin in that coordinate system squared.
Yeah, if you want to like
See what I mean?
check
This is just a
your
convenient
work
one.
on the
And I'm saying
sure
that,
no
oh,
search
I know that the
model
polar
should have,
coordinates, these
within
relationships
the-
hold on
that
that
group.
This
Okay,
can work for
perfect.
yourself.
I'll just go through it because physics is shut. I just really want to.
Are you looking at
I
the
want to
reset?
get this piece set done.
I
Yeah.
saw the light integral. This is gonna be so light.
It is going to be like. I just want to get this done because I need to prep for the.
No, I
X
think
and
this
y
should
go
be
from
like
negative infinity.
a lighter
X and y
one
go from
real.
negative infinity.
No more.
But that's
It's
saying
18
that's
today.
saying all
She's
this
in a
empty space.
From today.
And all of these spaces are.
I know, but I'm scared.
All
I
of
need
these
to
spaces
recover
are
the
Cartesian coordinates is x and y
I
go
could,
from negative infinity to infinity. All of
I'm
these
thinking
spaces,
of doing
the polar
like
coordinates is
an officer
r
for the
for all r's.
remaining 8, 2
All
materials.
and theta for all samples. And then theta is for that's how you do that.
But I'll message out about
R
that.
is okay. You don't put a sign, a
And
negative sign
also-
of r because
It's during the same time as the
the
physics
direction of the
final,
r
right?
is taken
The
care
AC.
of.
Oh yeah, I have to move it.
Yeah, you
Try to grab that into
get on that sooner rather than later.
No, I will.
Probably
It's very
mad at
good.
you about it.
Something.
You've actually seen it before because the single variable version of it is e to the negative x squared.
I don't want to do it. I want to wait until he does it.
So what's the 3D version?
excited.
Can you just finish it from here?
I
Is this in
I know
3D?
what it evaluates.
I meant in Polar.
This has to become.
Oh,
Like, do your
I mean, I could call this negative r squared.
Pi e to the negative u.
It's that. It's the little bell. It's the little bell curve in free space. This knows that r is x squared plus y squared. So this is just that r squared is x squared plus y. It's that same idea. And this gets used a lot in. So this is called the Gaussian because everything's named after Gauss. And one of the really cool things is in image processing, there's something called a Gaussian blur. I've never done Photoshop. And the way that it blurs pixels is by.
Oh, it's like, it's almost like 3D blur, like for time? I heard about it.
Quite, but it's that same idea. So wait. Oh, I need to put the exponents in the right place. X squared minus e to the negative x squared plus y squared. There we go. So this is a 2D way to see that 3D function. The color is the third variable. So red is where it's big, blue is where it's low, right? And so you can imagine that as like a little drop off. When you do Gaussian blur, what you're doing is you're taking every pixel and you're doing a weighted average of that pixel and the pixels near it, and you're weighing the neighboring pixels according to this function. So you're weighing the nearby pixels more than the distant ones. And if you do that, this is a picture of an old man. And if I go to blur, Gaussian blur, that's what I'm doing. It's different from other kinds of blur. There are blurs that weigh all the surrounding pixels equally. That's called a box blur. And it just gives you the average of the nearby pixels. Gaussian blur weighs the stuff near you more heavily. And that comes from that, and that comes from that. And so, yeah. Yeah, and it shows up in statistics as well. This would have made a neat piece of probably.
You should have made it a piece of, instead of a statistical program, you should have given us the Gaussian and rederived the normal CDF function. It's so possible with the Jacobian. It's so fun. I did it by statue.
So you did it, or did you and ChatGPT do it? Wrap it up.
I did it. I just Taylor expanded. How do you think the error function is?
During my interface, this was actually a piece of problem. So I was kind of embarrassed that I didn't remember how to do it.
Can you finish it off? I'm curious with the integral.
Oh, you're curious, aren't you?
You haven't done it?
I'm very curious. I want to see you.
Yeah, you're so curious.
I didn't know what I would do differently, but I'm going to go U-Sub.
Can you do, and then multiply by that number, whoever wrote that.
Whoever wrote that, right?
Genius probably also knew, but
What is the Louise?
try to do something.
Oh, it's going to be like 0.67 or something. It is a weird number to put in there. Because it's not just the normalization constant. I'm convinced it's not. Okay, so, all right. Well, I'm going to write it, but you guys help me out. What are you going to do U-Sub? So U is going to be what? Negative R squared?
Or just R squared.
Just R squared, okay. So du is 2R, 3R. Wait a second. Yeah. So 1/2 du.
Because that would be like.
R dr, so that can become pi
I wanted to
integral from, what are the bounds on U now?
I
0 to
think
infinity.
I was telling Dave, but I wanted to
That's
like
R dr, so that's
an officer
1/2
that it's there
e to the
tomorrow.
negative u.
Piece of material, because
Okay.
some people are trying to like.
And then what do we get here?
So I want to talk
That
about
1/2
basically
goes
the
away,
remainder
you
of
said pi.
8.2.
E to the minus 2, what do we get from this integration?
So this, I find like 2 hours and be like.
Negative
I know that just shouldn't people have like health resistance. When does that wrap up? Like
I dropped it. Oh yeah, it's a 5. It's a.
U0, that's
Like you get
pi.
ends at
Negative pi. E to the negative infinity
5 to 7.
minus
5, okay.
So it's at 5 to
1.
7.
So maybe if I did like,
You did 5 to 7 one day.
What's e to the minus infinity?
I don't know what y'all use for it. If I did like 8.
Whatever the
you'll
infinity
show
which
up
goes to
for
0.
that, or should I
This
just like
Monday?
earlier?
This is
What if
pi.
you this Monday and Tuesday?
Yeah, it would be like this upcoming.
Time, and now you want me to do pi times.
You
Is this under today or now?
Oh, that's right. You're
Oh,
right,
this
you're right.
week, because I'd want to like,
Okay,
I'd probably do
so
like
root
1
pi
earlier, and then I
times
do it minus
37.8.
happy it'll show.
Oh,
5 to
75 was
worry.
I'm about to get trolled in that. That's funny.
That night?
Okay.
Okay, alright.
Because P sets due on Tuesday.
Oh, yes, yes.
Screw
So 5 to 7 would make sense.
For
root pi
For today and tomorrow,
times
technically, I guess, because if you do it today, it's 7 would make sense for tomorrow.
37.8.
Okay, 5% would do because then I can
Oh.
actually get.
6, 7! Ah! Very cool.
But
That was my I love the Gaussian.
No, I'll probably do a couple of them because I
That's
think
funny, wow.
I want to get a gauge on what people are actually wanting to learn.
All right.
Yeah, 'cause it's
That made my morning. Thank you guys. Thank you. What are we playing for this? For you, Dave?
It was Sadie.
Yeah.
It was Sadie.
It was Sadie.
I saw you people out there
I'll
like
do
a
a
pizza.
couple.
Like,
No.
you're up to no good now.
People will click it.
Okay, I'll make an announcement. And then you wanted a
I had
lecture
too much
notes.
fun with this.
well, I was gonna. I'm having second thoughts about it too.
I do have a piece out.
I think work on the piece for now, and I'll send out the
Asshole last week.
Yeah.
Wait, how are you feeling? Can you get
And it's gonna hit me now, so I want to delay. So whatever you had, it's coming from me. What's up?
No, just about the like balance for dx for that. Would it just be like the radius plus like 1/2? Because that's the amount it's offset from the origin.
Oh, you're talking about oh, this guy.
Yeah.
Yeah, the bounds. So I mean, the way to do this one, let's do it in Cartesian coordinates.
Oh.
We can go polar too. I have a feeling the polar is going to be really annoying. Because it's not. Oh, then let's go Cartesian. Okay, so what variable do you want to integrate with respect to first? Y or x? Okay, so let's do y. So we enter this, and to get y here, what do we need to do?
Just
Solve it, yeah. So, and it's going to be the negative piece of it. So it's going to be what, 9/4 minus x minus 1/2 squared, square rooted, and then minus. And we're going to go all the way up to the positive version of this. That's our inner bounds. Or our inner bounds of our double integral.
Yeah.
And then our outermost bound is going to be y going from this value to this value. And what is this value? What is the x-intercept?
-1/2.
This is -1/2?
I think so. Wait, no.
Wait. Oh, I know that one of them is, wait, no.
Wait, I think it's negative. It's very far, so I think it's -1 and -2.
Negative, yeah.
-2.
-2.
Negative 1 and 2. Sorry.
-1 and 2. Okay,
Yeah.
let's get 9 if you like that.
Okay.
So if y is 0, to get, this needs to be 3/2. So 3/2, that would have to be -1 minus 1/2. Yeah, so -1 here for sure. And then 2 minus 1/2 is 4. Yeah.
Okay.
That was fine.
Yeah.
Yeah. And I want to make sure this is clear. We would give you a nicer circle for an exam problem or something.
How would you solve for R if you were trying to do a polar?
Okay, so we have r times r, because you know what I would do? I would actually solve for, what's easier to solve for here? It's easier to solve for theta. Yeah, yes. Because theta would be 2 minus, sorry, it would be, I'm going to move variables around in the equation. So, solve this for theta. So, solve this for cosine of theta. We got 2 minus r squared over -r, which I want to make this, so r squared minus 2, which is r minus 2 over r. So I would make my bounds of theta arc cosine of r minus 2 over r.
0 to that.
Right, that's the bound, and actually theta, so theta would be probably from minus this to this, right? Because you're going from, oh, that is so annoying. What would you
But you
actually, yeah, go ahead.
you just take an equation with R and with the new radius, and you just kind of solve that and move it around so you get something for R or theta.
And I think maybe solving for r is better, because what should your bounds be in theta, actually? What do they have to be?
0
Or across the whole thing, wouldn't it be all of the circle? I think it would have to be 0 because r is only positive, right? The only way you could get here is if you ended up, so I think, yeah, your bounds in theta have to be 0 to 2 pi. And then your bounds in r, that's where it gets fun. I think there will be some analytical solution to r here or something.
Oh, okay.
My guess is this is not, unless I'm forgetting something. I don't think this is ever a pretty one. Oh, you know, oh wait, ha! I know what this is. R squared minus r, no, r squared minus, I'll write it in a way that is more explicit. R squared minus cosine theta times r minus 2 is equal to 0. What's staring at us? A polynomial in R, a quadratic. Right? R squared minus something R minus 2. How do we solve an equation like this, a second order equation? Forget trigonometry, just think of this as like x squared minus something x minus 2. Quadratic equation.
Okay.
Scary. But yeah, that's
And
what
then you get 2 answers, and then based off of like logic, there
it's
is
the positive.
one.
Yeah, because R in our system is positive, yeah.
Okay.
Yeah.
Okay.
If I wanted this problem to be nice, what would I have chosen my plane to be? Probably not x plus 2. Maybe Yeah, what would make it so the completing the square would give you a nice thing? I think there would need to be a coefficient here, maybe of 2. That's my guess. Because in general, for a circle that is off-center on the x-axis, a circle of radius a off-center on the x-axis by an amount a, its r is 2a cosine theta. That's this.
Oh, yeah. Okay, yeah,
And those are the, that's as scary as we will go.
okay.
You know, and what do you think the version of it would be if it were offset on the y-axis?
2x.
You did all right, Sherry? Okay, because last week, since I couldn't see your face through the mask, I'm like, she could be panicking, she could be happy, I have no idea. So I want to make sure you were okay.
She was go. I was working on this with her Saturday night.
Did you got it?
Amazing. Yeah.
Very cool.
No, you were amazing.
Awesome. All right, you guys. I'll try to be less sleepy next Wednesday.
Sorry.
Take care. Also, I think that was a mess. Like I think I fixed it maybe toward the end of the program.
I think they were getting it.
They were getting it. The question about the plane and the intersection was really good. I think I could slow down and try to solve it.
Yeah. MIT class result said it's the most unusable thing in the world. Oh yeah, can you hit end on that? Red button.